All right, let's talk about databases. We're going to build a mental map of this whole world, moving past all the confusing brand names to get to the real heart of it. Why are there so many different kinds of databases in the first place? Let's dive in.
So if you've ever been anywhere near software development, you've seen a list like this. PostgreSQL, MySQL, Redis, MongoDB. It's just this sea of logos and names, right? It's totally natural to feel a little overwhelmed and just wonder, what is actually going on here?
And that brings us to the big question, the one we're here to answer. If these things all just store data, why on earth do we need so many different versions? I mean, isn't there one that's just the best one? Well, the short answer is a big no. And the reason why is what this is all about.
Okay, this right here, this is the key. It's the single most important idea to get. Don't think of these as competing products. Think of each database type as a unique, engineered solution, a very specific structural answer to a very particular kind of problem. Once you see it this way, the whole landscape just clicks into place.
So, let's see how these different answers get built. And to do that, we have to start at the bottom, with what they all have in common, the foundation.
You know, what's kind of wild is that when you strip away all the marketing and all the complexity, every single one of these databases is built on the exact same physical stuff. We're talking about storage, like a solid-state drive, memory, RAM, and a CPU to do the thinking. That's it. There's no magic hardware.
So the crucial point is, the difference isn't in the metal, it's in the ideas. It's all about the architectural choices, the software decisions about how to organize the data on that hardware. How should the data be shaped? How do you ask it questions? And most importantly, what are you optimizing for?
And that lets us start our tour. We're going to look at a series of common data pressures, the tricky problems that engineers run into, and for each one, we'll reveal the specific kind of database that was literally engineered to be the answer.
Our first pressure is a huge one, the need for what I call structured truth. Think about any system where being correct is non-negotiable. We're talking banking, e-commerce, any kind of business logic, where if the numbers are wrong, the whole thing falls apart. The data has to be consistent, period.
And the classic, incredibly powerful answer to this pressure is the relational database. If you've ever heard of SQL, well, this is its home. This family has been the king for decades, and for a very, very good reason.
So, relational databases organize everything into these super neat tables with rows and columns. Think of them like a collection of perfectly structured spreadsheets that you can link together in really powerful ways. Their absolute superpower is this thing called transactional safety. It's a guarantee that a complex operation, like moving money from your checking to your savings, either happens perfectly, all at once, or it doesn't happen at all. It will never get stuck halfway. That guarantee is everything, but it's a choice that comes with trade-offs.
But what if your problem is completely different? What if you don't need all those complex guarantees? What if the only thing you care about is pure, unadulterated speed for a really simple task? Like, you need to grab a piece of data in the blink of an eye. That's the pressure of Fast Simple Lookup.
The engineered answer to that is the key-value database. This family basically throws all that complex structure out the window. It is built for one job and one job only, getting you a value, lightning fast when you already know it's key. I mean, the model couldn't be simpler. It's just a giant dictionary. You have a key, say user123, and it points directly to its value. That's the whole game. This super minimalist design makes them insanely fast, which is why they're perfect for stuff like caching or managing website sessions. They trade away all that structural safety for raw velocity.
Okay, on to our next pressure. A lot of modern applications deal with data that's just, well, it's messy. It doesn't fit neatly into rows and columns. Think of a user profile. It's got lists, nested information, all sorts of varied fields. Trying to cram that into a rigid table can be a real pain.
And for this, we have the document database. Its whole philosophy is basically, don't fight the complexity, embrace it. It's designed from the ground up to store data in a way that looks a lot more like the flexible, nested objects you actually use in your code.
Now, let's take a big conceptual turn. What if the most interesting part of your data isn't the individual data points themselves, but the web of connections between them? What if the question you need to ask is, how are these things related? Or, what's the shortest path from here to there?
This pressure, this need to find connected meaning, it gives us one of the most powerful and, frankly, coolest answers in the whole database universe, the graph database.
See, graph databases don't think in tables. They think in nodes, which are the things, and edges, which are the relationships that connect them. This model makes them unbelievably good at navigating complex networks. It's no surprise that the engine behind social networks, fraud detection, and any system where understanding that web of connections is the whole point.
And the Tor doesn't stop there. There are other specialized answers for other pressures. If you need to find the most relevant document out of millions, you need a search-oriented database. If you're drinking from a fire hose of time-stamped data, like from IoT sensors, you need a time series database. And if your problem is just sheer mind-boggling scale, data spread across hundreds of machines, you'll look at something like a wide-column database.
Okay, so let's zoom out and put our map together, because the fact that all these different answers exist points to a really crucial idea. It's all about trade-offs.
And this is really the punchline of this whole explainer. There is no magic database. There is no one-size-fits-all best. Every single time a database is engineered to be great at one thing, like rigid consistency, it is actively choosing to be less great at something else, like flexibility. They are all bundles of trade-offs, which is why real-world systems often use several different kinds, picking the right tool for the right job.
And here it is, our map, all in one view. You can see the choices so clearly. Relational aims for correctness, key value aims for blindingly fast retrieval, document databases aim for flexibility, and graph databases are all about traversing relationships. Each one has a different target. Each one is a different piece of machinery.
So we land on this final simple truth. We have a rich world of databases because we have a rich world of data problems. And you just have to choose the structural machinery that is actually designed to solve your specific problem.
And this leaves you with a really powerful question you can take with you. From now on, whenever you hear about some new database, don't just ask, what does it do? Ask yourself this instead. What kind of data pressure is this system specifically engineered to handle well? Because that question, that's the key to the entire map.